Hi. So I want to spend a video talking about the theory behind regression and making sure that conceptually everything makes sense. So the idea behind regression is that if I give you a bunch of data points, let's say I give you a bunch of data points, I draw them kind of far out. I see this. And if I were to draw some line that goes through the data points somewhat, ideally that line goes through all the points, but we don't have that luxury in this case. We try to find some line f of x that is our line of best fit. Our line of best fit. And this is our regression model, our linear regression model. In this case, because we assume that f of x was a line. So if f of x is a line, that means that this equation f of x is something like y equals mx plus b, but we'll generalize that to be some slope times x plus a naught. So a1x plus a naught, where a naught's the y-intercept and a1 is the slope. Now, ideally, if I were to draw a baby version of this, and let's imagine that I had points that were like this, I might get lucky and end up with a perfect line that goes through all the points. This is our ideal situation. Well, ideally, f of x goes through all points perfectly, because that means that we did a good fit. Our fit goes through all the points as expected. Now, we don't have that luxury a lot of times. A lot of times we are completely off, kind of like the picture that I drew here. So what we try to do is we want the distance between the dots and our red line of best fit to be as close to zero as possible. Down here, the distance between a point and f of x is zero. When I say distance, I mean the vertical distance, the y value. So if you were to look at, let's say, at this case, this is the distance between the function f of x and the blue data point. This is what we call the residual. And I've been calling that e sub I in notes. And you can see that at every single point, we're going to have some residual. Where the definition of the residual is that it's the data point minus the function value at that location. So e sub I is y sub I minus f of x sub I. Conceptually, what we're doing is we're grabbing one of these data points. So let's say we're grabbing this one at the top. This occurs at some value, xi. And at the function, there's some function value there. This is f of xi. We plug x of I, maybe x of I is 3. I plug it into our fit. We get a value for x equals 3 on the fit. Maybe it's 3, 7. And our data point is 3, 12. There's some distance between them. And that's what we call the residual. Ideally, what we want to do to get our best fit is to minimize the sum of the residuals. So I call that S sub R. And what I'm going to do is I'm going to look at the distance in between every single point and the curve. And remember, this curve we're trying to find is unknown. We don't know what this red curve is. We don't know what A1 and A naught are, because this slope or this line could be anything. It could have been like this. It could have been like this. I'm not sure. The A1 and A naught are the unknown things that define the shape of the line, and they are unknown to us. So we have to find those coefficients that yield the best fitting curve. So the way to do that is to try to minimize all the residuals. We say that the residuals are the sum, and we'll have one for every single data point, so from 1 to n. And I will say y sub I minus You know, let's go back a step. Let's make it even more general. We're going to sum all the residuals. Now, the thing to note is that if you look in this case, you know, this residual and this residual might cancel each other out because we see that one of them is positive and one is negative. So to help alleviate that, what we do is we end up squaring the residuals, because therefore everything will end up becoming positive, and we'll just take into account the overall distance away these points are from the red curve. So we will sum up, so really we're doing this of residual squared. That's our addition. Be y sub I minus xi, that whole thing squared. So again, y sub I are these blue data points, and fx of I are the red data points at the same x location. So if we were to do some sort of linear fit, depending if it's a1 x plus a naught, we would substitute that in there. We would sub in any function that we are trying to fit to the data. So let's say, for example, I give you a different data set. Let's say I give you data, maybe that looks something like this. I'm just improvising here. I say, you know what? I can have a line go through this where the y-intercept is 0. So I say that this function here is equal to a1 x plus a naught. I'm saying that a naught is 0. So what that means is we're going to say that our sum of our residuals squared is a summation of yi minus our function, which is a1 times x of I squared. This is the function at x of I. Our general function just a1 times x, but specifically at some coordinate x of I, which could be x1, x2, x3, whatever. We're comparing that to y1, y2, y3, ultimately. We're finding the function value at that location, which is what fx of I is. So our only unknown is a1, because we need to find the slope of the line that best gives us this fit. So what we'll do, ultimately, to find the value of a1 that yields the minimum sum of the residuals, we will take the partial derivative of this function with respect to that unknown variable. Now, what's nice about this, if we come back to our series rules, like what this looks like in general, is we take the partial derivative of the series, and it looks like, oh, we have to do the whole series first before we can take the partial derivative. But because each of the series terms are being added together, we can apply that partial derivative to each term individually. So what that ultimately means is that we can take the partial derivative and bring it into the summation. And like we learned about in regards to minimization, we're going to set this equal to 0. Basically, if you think about this S of R, you know, as being some function that depends on a1. But if I plug in some a1, xi and yi are fixed. But if I plug in some a1, I'll end up with a different SR. And you're going to end up with some sort of curve that looks something like this, ultimately, where there's a minimum. And this is the best a1. And if we look at this DSR dA1, that's basically the slope of the line. There's an ideal point where that slope is 0, and that's going to yield our best a1. And that's why we set this equal to 0. So if we take the partial derivative with respect to a1, we see that we have this function here that depends on a1 with an exponent. So it's going to be a chain rule type of thing where we pull down the 2, and our inside remains the same. And then we multiply by the derivative of the inside, the partial derivative with respect to a1. Well, this yi doesn't have an a1, so that's just 0. And the partial derivative of this with respect to a1, well, there is an a1, The thing that's held constant is xi, or negative xi. So that will end up spitting out a negative xi from our chain rule differentiation. So we can see that there's a -1. That's with the xi. We can take that out with the 2 and write this as -2. The summation of yi minus a1 xi and xi is equal to 0. You see what I did? This negative is a -1 with that 2. I took that outside the summation because that's just a constant that's being multiplied by every term. I can factor it out. And because of that factoring and the fact that it's equal to 0, I can end up canceling it out. So this is going to be the summation from I equals 1 to n yi minus a1 xi times xi is equal to 0. I'm going to distribute that xi to those other terms because that wasn't there before. The benefit of distributing that is that we will end up with a subtraction of 2 terms inside the series. And the benefit is that we can apply that summation to both of those terms individually. So this will be the summation of yi xi minus the summation of a1 xi squared. And that whole thing's equal to 0. Where this minus sign here came from that minus sign. Constants come out of the summation, just like the 2 did earlier. So we can take the a1 out. And we can move this guy over to the other side because it's negative. We took the a1 out. And now we can solve for a1, because remember, this is just a number. The summation of xi squared is the summation of 2 squared plus 7 squared plus 12 squared, whatever the x values are. It just ends up being a number. We can divide by that number. So we end up with a1 as being the summation of yi xi over the summation of xi squared. And this is our best slope for the regression line without y-intercept. So basically f of x is a1 times x. And we'll do one example of this. I'm just going to make up some numbers and see what this fit ends up looking like. We'll just do an example. See how properties end up being. I do 1, 3, 6. We'll do 2, 3, 5. I'm just making up some points here. So if we were to go ahead and try to graph something like this, see if I can do this nicely. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. We have 1, 2. Do a different color. 1, 2. 3, 3. 5, 6. So we kind of see that there's some linear thing here just based on these random numbers I made up, but it won't be perfectly linear because the slope changes between the points. So we're going to fit a point f of x equals a1, fit a function rather, f of x is a1x to this. So what we'll do is we know what our equation for a1 is. We just found that was a summation of xi yi over the summation of xi squared. Yep. So in the numerator, it's summation of x times y. So what we'll do is we'll multiply x1 times y1 plus x2 times y2 plus x3 times y3. And again, I'm getting those from the table. And now I'll go ahead and I will add the values of the x values squared. So this is going to be 1 squared plus 3 squared plus 6 squared. So if we look at the numerator, that's going to be 2 plus 9 plus 30. Before I use the calculator, 2 times 1 is 2, 3 times 3 is 9, 6 times 5 is 30. 1 divided by 1 plus 9 plus 36. going to be 41 over 46. I did everything right. This is going to be 0.891 as our A1 value. So that means that f of x, forward fitting this is 0.891 times x. Now again, depending on what the function is, the math changes, but this procedure is exactly the same. We're going to submit that function into this least sum squares. Remember, this is least sums, or the least squares method, where the idea is that we'll take our function f of x, whatever it may be, that we are trying to fit the data to. We'll subtract it from y sub I, square it, and then take the partial derivative with respect to any sort of unknowns. If we have two unknowns, I'll have to take the partial derivative twice. That'll lead to two equations with two unknowns that we can solve for. But that's the idea. I hope that this makes sense. Please let me know if it doesn't. Thanks.